All right, let's go for it here. This is Chapter 7. We are just starting with the first section here. It is called the Law of Sines, and really what we're trying to do here is we're trying to figure out how to solve for each piece of a triangle. And so we have, if you think of a triangle in your mind here, you think of 3 sides and also 3 angles, and that's what we want to do here. So the Law of Sines works for a few cases here, and we'll figure out that one. And there's one case that it does work, but we got to think about what's going to happen here. So think back to your days in geometry in high school here. If you think back, you used 4 different ways you can make congruent triangles or prove that triangles are congruent. And it was the ASA property, the AAS property, the SAS property, and the SSS property. These 4 show that 2 triangles are congruent. Well, because 2 triangles are congruent, it only makes, really in a sense, 1 triangle, or has the possibility of making a triangle. We're going to use this whole concept in which we will, if it's this kind of property, it will allow us to derive 1 unique triangle, and with that we can find all the different sides. Alright, so the law of sines, which one does it work on? Well, the law of sines works on this first one here, the ASA property, and we'll see how that works. And then also works on this one right here, these 2. And then we're going to figure out an ambiguous case, not part of this list, but we can sort of still derive maybe a triangle from here. All right, then the question is, Mr. H, how come these bottom 2 right over here? What's up with these 2? Well, these 2 have to do with the fact that we're going to learn in the next section. It's called the law of cosines. So the law of sines works for these above 2 and works for another 3rd case. Kind of what we just mentioned here before. It kind of gives you a delineation of each of these cases here. So for the AAS and the ASA property, what we have is really have, in a sense, we have 2 angles and a known side. For the SSA property, it just kind of defines it. So you have 2 sides, and then you know the next angle after that side. Here you have 2 sides, but you know the included angle, and this one you just know all 3 sides. Let's start it here. So the law of sines really is derived from having 2 things that equal h. If you think back to the days in which we were doing right triangles. Let's see if I can fit this onto the screen here. If we take this one right here, if we take this angle here, we generalize triangle here. This is a generalized triangle right here. And we drop an altitude down. Then we just label this as h. Well, we have a few things that we know. According to the definition of sine, sine is opposite over hypotenuse. So if I were to derive this, I would say this. I would say the sine of A is equal to opposite over the hypotenuse, in this case, which is this b value here. So if I want to, I can actually get rid of this. I'm going to multiply both sides by b. This gets rid of it. Notice we have a relationship to h. Well, we can also do it another way as well. And so if I pick a different color here, I can look at angle B. And so if I say, look, hold on, sine of angle B is opposite over the hypotenuse. So opposite is the h, because again, h stands for height for us, not hypotenuse, over a. A was just the hypotenuse of this triangle right here. If we were to make this triangle, B, then this one right here is the other triangle right here. All right, and if we multiply both sides by a, then we get this derivation right there. So really, notice h is equal to this, h is also equal to this, and it's the same exact h. So if that's the case, we just set each of them equal to each other, and we have ourselves the law of sines. Law of sines has, in a sense, a correspondence between an angle and its opposite side. And that ratio is the exact same ratio between another angle and its opposite side. That's pretty much it. So you can write the law of sines a few different ways. You can write it as this right here. You can compare the B and the C. You compare the C and the A. You can compare the A and the C, whichever way you want to write it. Law of sines also given various ways. You can write it as Again, the three different pieces, that's the way we normally do it when we're calculating things. You can also flip them upside down and notice the reciprocal relationship. You can write the a on top, the sine of a on the bottom. Again, all this still is the exact same thing. So let's go for it. Let's try a problem. Let's see if we can solve this one here. So normally a triangle is labeled as ABC. You go counterclockwise. Not always, but that's the normal one if you sort of you want to draw a general triangle. Okay, what do we know? We know angle A is 70, angle B is 65, and then little a is 16. So first things first, what we want to do is we want to find all the pieces of this triangle. I want to find all three angles, all three sides, and the easiest thing to do is just to find angle C. And so we do this here, we just add up the two angles that we know, and we know that the interior angles of a triangle always add up to 180, therefore let's subtract that from 180, and then we will know exactly what angle C is, which is 45 degrees. That's cool enough there. Awesome. Done. Now we look at the law of sines. Okay, since I know that angle C is 45 degrees, I got that. And then I also know, hey, look at this relationship here. I know an angle and its opposite side. Then I also know an angle and I don't know its opposite side. So I can figure this correspondence here, or this ratio between the sine of this angle and that side, has to be exactly the same between the sine of this angle and this opposite side. So there's something we don't know. All the other three pieces we do know. That's cool. Let's go for it then. All right, so we're going to set up this little sine of A over little a is going to give us sine of B over little b. And with that, we're going to, okay, so we got to do this here. We got to solve it the way I wanted to plug it in. So I'm going to solve it for little b, since that's the one thing I don't know. So I'm going to multiply both sides by AB to get rid of the fraction. So the A cancels on one side, the B cancels on the other, but pretty much I got rid of my fractions here. And then, since I'm trying to solve for little b, I'm going to divide both sides by sine of A. And here's what I want right there. All right, now let's plug in whatever we need to plug in here. So little a I know is to be 16, sine of 65 degrees over sine of 70 degrees. All right, punching that into a calculator. The only thing you got to be careful for is to make sure that you are in degree mode on your calculator. Degree mode always, if not, then you're going to get the radian answers, and that's not what you're looking for. All right, plugging it in. See if you guys got the same thing I got. I got 15.4 inches. Let's label our inches right there as well. Cool. All right, so I know angle C. I know this side here already, and so I guess the only thing I don't know is this little c on this side. So let's make that relationship. Now you could use angle B and its opposite side. The only thing I recommend not doing it is because this is already to the nearest tenth. It's in a sense already approximated. You would want to use the stuff you know for sure and exact value. So I know that's exactly 70 degrees. I know that's exactly 16 or 16.0. So it gives you a more closer approximation. All right, so let's go for it here. So sine of A over little a, sine of C over little c, and I'm trying to find little c. So here we go again. We're going to multiply both sides by AC to get rid of fractions, and those cancel. Leaves us with C sine of A. On the other side, the C's cancel, so it leaves us with A sine of C. Since I'm solving for little c, divide both sides by sine of A, and that's what I'm going to plug into right there. Plugging into A sine of C over sine of A. So I got 16 from the previous slide. I got a 45 from what we calculated on the previous slide, and 70 from what was given to us. Punching that into a calculator, I got a 12.0 inches. All right, this is the way I did a little snippet of a TI-83 calculator. Right there. So this is the way I would plug it into the calculator. Make sure that you're plugging in correctly here. The one thing that you should have is you should have these little parentheses. Once you put in that 45, when you put sine of 45 degrees, make sure you close off that parenthesis because that's for the angle. If you want an extra parenthesis on top just to kind of keep the 16 and the sine of 45 together as one piece, that's fine as well. But eventually, hopefully your calculator gives you what I got, which is 12.0 inches. All right, how about an application question here? So we're going to figure out, looks like we're going to figure out, you can read it for yourself here. We're going to figure out a height of a mountain peak. So let's go for it here. So from a plane and level, angle of elevation to peak is 40 degrees. So you're standing on the bottom of the mountain. So let's draw a little mountain area here. Boom. You're standing on the very bottom right over here. I put a little zero or funny little our eyeball where we're looking from right there. And we say 40 degrees. And then what happens is you move back from the mountain 2,500 feet. Then you look again, and then this time the angle of elevation is only 35 degrees. Well, that's all we need right there. Notice we just have two spots, and we know the distance we traveled. We can find whatever we need at this point. This is done for mountains. This is done in surveying. If you see those guys, Caltrans workers with reflective jackets, and they have this little yellow equipment with them, and they're doing laser approximations. That's exactly what they're doing right here. This is almost the same thing. Anyways, how do we know the height of this mountain? Let's go for it here. Let's see what we can figure out based upon the stuff here. So first things first, I'm going to drop an altitude down from the mountain. That is eventually what I want to solve for. And then I also know if I have 40 degrees on this side, I know that the supplemental angle would be 140 right here. Ooh, that also tells me some stuff. Since this little triangle is its own little triangle, then I know that 35 degrees plus 40 degrees is 175. That means this guy would have to be 5 degrees. Okay. Now we're going to use the law of sines. Notice I have a correspondence between an angle and its opposite side. And then it doesn't matter which one you choose. You can use the 35 degrees and get this line right here. All right, you can choose to get, let's see, 145 degrees and this line here, except then you're going to think of this big triangle here. Either way is going to work just fine. What I'm going to do, I'm going to use this one right here. I'm going to use this little guy here. So sine of 5 degrees corresponds to 2,500 feet. And the sine of 35 degrees is going to correspond to x. And x is this one right over here. This is what I'm going to shoot for. Again, doesn't matter which one you wanted to shoot for. If you got this big black line here, then you still could do the same thing and get the height. All right. Looks like I'm going to solve for x because that's the variable I don't know. So I'm going to just multiply to get rid of fractions here. The 2,500 goes away, so it's x sine of 5 degrees. This way is going to be 2,500 sine of 35 degrees. Eventually divide both sides by sine of 5, and I think I have this as my plug-in value right here. Again, pause the recording if you think I'm going too fast. You can always pause me. I'm just kind of doing this real quick here, and then but you can stop me anytime. All right, plug this into a calculator. If you got it good, you should wind up with 16,452.63. That's where we're at here. Okay, based upon that, now we have this little relationship here. It's this little small angle here, the x that we found, the 40 degrees on the bottom. And we're going to now use the definition of sine to get what we're looking for here. So in fact, I'm running out of space here. Let me read it. Let me go to the other side here. Let me go to the other side. So I'm going to rewrite this here. I know 40 degrees. I know this side here. And now I'm going to figure out h. I'm going to figure out the height of this mountain here. All right, now I'm not using the law of sines here. I'm just using the definition of sine. Sine is the angle to the opposite side, h, over the hypotenuse. So that's the definition of sine in the first place. All right, multiplying both sides by 16,452.63. Multiplying it by sine of 40 degrees, punching on a calculator here just to make sure you know that you have to use degree value in the calculator here. And we get an answer of 10,576 feet because it's 5.5. And if you want to look back, this is my calculation for the law of sines from the previous slide. That's what I got there. This is my calculation for this slide over here. So there's that stuff given. All right, now we move on to the ambiguous case. There is one case where we could not use in order to make congruent triangles or prove congruency of triangles. And that case was if you know two sides and you know the next angle. So if you knew this angle in the middle, it would be SAS, and that would be fine. But this case right here, this is called the ambiguous case, because sometimes it could not be a triangle, sometimes it could be one triangle, sometimes actually it could be two different triangles. So it's kind of a little bit difficult to sort of see at first. Eventually, you kind of get used to it. But there's a test that you sort of have to do. All right, let's go for it here. So what is the test, or what's the different case that you can have? Well, it's based upon the fact that we know this angle, we know this side to be a certain amount, and then we know this side as well. So angle, side, side. And here's the first case. It's the no triangle case. It could be that this angle here, this side here, is going to be up high, very high up here, based upon the angle and this. And then A is too small. It's too small of a amount to actually even reach the bottom here. So if you say this, if A, we're going to do our test points. If A is less than H, now hey, what does H come in? H is the definition, right? If you have sine of A, this is just the definition of sine. If you say this here, okay, so definition of sine would be sine of A is equal to opposite side, right? Opposite side over hypotenuse. And if you multiply both sides like this by B, you notice the B sine of A is going to give you H. H is, we call it the minimum that is required to get back to, if you're starting up here, H is the minimum required to eventually get back to this line here. Right. So if that's the minimum, this brings us case 2. If I know the angle, and if I know the side, and if H is equal to A, that means I barely just got enough minimum to reach back to the other side. I get myself a 90-degree triangle, and therefore I have one triangle. In fact, it's a right triangle. It's only one possible case there. All right, and then the next case here. This is case number 3. I know the angle. I know its side, and then I know the A value. I still compare it to H. So notice here, I don't even need to compare it. Well, yes, I do need to compare it to H. But H is less than A, which means I have enough. A is bigger than what I need to get from one side. So real quick here, I'm going to draw H. H, let's say A goes down this way, right? And A is not small. In fact, I don't know why that red line appeared here. So it should be like this. You go down here, that would be the minimum to form a right triangle, but then A is actually even longer than that. So if it's longer than that, here's the fun part. This is where you get two different triangles. So A could swing this way, and notice it's on the line still, right? Or A can swing this way. And because of that, you form yourself two different triangles. You have to solve for both triangles. All right, there's that case. Next case, and the final case for the acute triangles, is if you have an angle, and you have the B value, and then you look at the A value. The A value is actually even bigger than the B value. In that case, you just have one single triangle, because if this was to swing all the way back over here, it would go all the way here, and that would not even be the same triangle anymore. So, so there it is. There's your acute triangle cases. All right. For the obtuse angle, so there's only two cases. These are the easy ones here. Obtuse angle says this: if I have the sine of A, or the A angle, I know the B, and I know A. I just need to compare the A and the B together. If A is smaller than B, there's no way I can even reach this side anymore. So done. If A is exactly the same as B, I still don't have a triangle, because then it just comes back down to here, and there's no extra piece to form a triangle this way. If A is bigger than B, then there's only one case. You get yourself a one triangle. That is it. All right, let's do some practice problems. Oh, here's the different cases. Again, if you want to go back in the textbook, I'm sure this is in your textbook as well. Here's your cases for none. A is too small, doesn't even make a right triangle. A is the exact same as B sine of A, that forms one right triangle, barely enough minimum to get back to the third side. A is between the value of the sine of A and B, and then A is larger or equal to B, which means you have yourself one triangle. That's the acute angle case. And then with the obtuse angle, you're just comparing A and B's. All right, so let's go for it here. First things first, how many triangles can be drawn? So we're not solving for the triangles yet. We're just trying to see how many triangles we're going to have in the first place. Okay. And the first thing we want to notice is, do we have an acute angle or do we have an obtuse angle? In this case, 35 degrees. That is an acute angle. So I'm going to draw it like this. I'm going to draw it like a small angle over here on the bottom. That is going to be 35 degrees here. That's the A value. That's cool there. Then we have ourselves the B value, the C value. All right, the B is 6.5 and the A is 3.5. Oof, okay, so here it is. We're going to try to compare this. So we're going to get, the comparison is B sine of A. Plug that in, 6.5, sine of 35 degrees, and we get an answer of 3.728 on our calculator here. All right, if this is the case, what do we have? Well, it says that the minimum required to go from B all the way to C would be 3.728. Now our A value is 3.5. It is too small. Too small here. If we were to really draw it according to at least scale, it would sort of look like this. It's 35 degrees here, 6.5 here, and 3.5 is right there. Not enough to form a triangle. So in this case, we have no triangle formed. We stop there, we say no triangle. If we were to solve this, we would say no solution, or we can say no triangle in this case. All right, practice problem number 4. Let's take a look at this here. Okay, so we're just trying to figure out the number of triangles formed. That's all we want to do. How many triangles can be drawn with A is an obtuse angle. There it is, more than 90 degrees. So if I draw this out, I'm going to draw it kind of like this. There's my 105 degrees here. A value. If this forms a triangle, then we're going to have a B value about right there. And then the C value is going to be up here. All right, that's going to be 12.5 is little b, and then A value is 11.2. And this one I did kind of draw to scale because the comparison really is between A and B. A is 11.2. It is not big enough to reach to this other side. So in this case, it's really the obtuse case. It's case 1 where A is less than B, or A is less than or equal to B, therefore there is no triangle formed. Impossible. All right, solving an SSS triangle. Okay, so now we're not just going to say how many angles there are, or triangles there are. We're actually going to we're going to solve it. Actually, we're going to solve this triangle then. Okay, let's go for it here. So I got now notice I don't know angle A anymore. Actually, I know angle C this time. So that's okay. What I'm going to do, I'm going to label the triangle a little differently. That's all. So then C is going to be down here. That's going to be 12. So let's see how this works here. And so I'm going to label this one as C, okay? And then since this is B, that means this would be corresponding to B over here, and then this would then correspond to A. So I don't know why this thing has these little weird markings that come up sometimes. Okay, there's that. That's my label. Okay, now the question is this. Is 12 enough? Is 12 enough the minimum to get us down there, to get us to that side? Let's check it out. Our test is sine of this multiplied by that. So let's go for it here. So 15 sine of 35 degrees. And if I do that, punch in the calculator, it becomes 8.6 inches. Yes, we do have enough. In fact, we have a lot more than enough. So this time, here's what happens. That means we have more than enough, but notice that A is still less than, C, so which is this, C is still less than B. So really what happens is, this is two different angles. I can bring this down here, and if this was stretched out further, it would hit this and make this little triangle right there. Okay, let me label it the way it's labeled in the textbook here. So I have B2 right here, but then it also can swing this way and still be 12. So this is 12 feet this way, but this could also come over here, and this would be B1. This would be another one, which it's still 12 feet, but it's on the interior or coming closer to the line. So there's my two different triangles. There they are. They can form two different ways. All right, so because of that case, here's what we want to do. We want to form, we want to at least start the process here. I want to at least know the angle measurement here. So here's what I want to do. I want to know this angle measurement right here for now. Okay, and then we'll start applying it to what we have here. I want to know that angle measurement. So let's see. Do I know an angle in its opposite side? I absolutely do. Do I know an angle? Well, I don't know the angle, but I know its opposite side. So there it is. I'm going to solve for this guy right here. I just want to see what that is. So let's go for it. Yeah, so sine, let me give you the formula here. Sine of c over little c is equal to sine of b over little b. Okay, and then you know what? I'm going to plug in the values I know here. Let's see. The values that I know is sine of b over 15 is equal to sine of 35 over 12. So let's see. If I multiply both sides by 15, I'm going to get 15 sine of 35 over 12. And then I'm going to take the inverse of the sine value here. So it's going to be inverse sine of 15 sine 35 over 12. All right, I'm punching that into a calculator. Again, be careful, make sure you're in degree mode. And we get ourselves 45.8 degrees. All right, what do I know? I know this guy is to be, or B2, actually we probably should label as B2. Sorry, let me go back real quick and label B2, 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 B2 is 45.8 degrees. All right, this guy is an isosceles triangle if you think about it here. This is an isosceles triangle here, because this is 12 coming down, right? And this is 12 coming down. So if this is 45.8 degrees, then therefore this angle inside here is also 45.8 degrees. Let's label that. So this guy would be 45.8 degrees, but the only thing is we don't want that angle. Who cares about that angle? Well, the angle that I really want is, let me see if I can just switch markers here just a little bit here. The angle that I really want is this angle right here, which is the supplemental angle to 45.8 degrees. And you got to calculate that real quick here. 180 minus 45.8. Do that on a calculator real quick here. And so that makes 134.2 degrees. All right, there are my two triangles. I got them that I have to solve for. And yes, I got to solve for both of them. So let's go for it. Let's solve this. So two triangles that I have. So solution 1, solution 2, if you want to do it that way. There's A. Let's see. There's solution 2 here. That's okay. So corresponding, again, it's a little bit tedious to go through this here, but I got it. There's solution 1, there's solution 2. Let's label all the stuff we know. C is 35, B is 45.8. 15 is there, and a 12. So I'm going to solve this one using the law of sines. And so the angle that I don't know is angle A, and that's easy to get since I know the other two angles within the interior of the triangle. All I got to do is add them up, subtract them from 180, and we get an answer of 99.2 degrees. We're good. Done. Well, almost done. Well, I know that angle, so I just need to know the opposite side, right? Let's see, I know I know the angle here, I know the angle there. I just figured out that one, so I have everything except for little a, which is right there. All right, let's plug it in here. So then sine of 35 degrees over 12 is equal to, and again, I would like to use as many of the stuff that I know, not approximated values here. So therefore I got this. What should I do here? I'm thinking, again, hopefully you guys can do this in your head. I multiplied both sides by a and 12, and then I divided both sides by a sine of 35 degrees. So we're skipping a couple steps here. I think you guys know because we've practiced this already. Punching that into a calculator, and you got yourself 20.7 feet, and that is good by me right there. That's the two things I know. Now let's jump to the other side here. 35 degrees. This was 134.2 from the previous slide. 15 and 12. And so then now we're going to do this here. We're going to add up the two angles that we know within the interior of our triangle. Subtract that from 180 to give us the corresponding A value. And as we do that, we get ourselves 10.8. All right, we're going to use that. Again, notice it's the same exact process. We're going to use that to know that corresponding little a value. All right, again, multiply both sides by a, and then divide through by sine of 35. Cross multiply. Technically, you're just cross multiplying, and then dividing by sine of 35. If you sort of want to see how that happens here, let me kind of show you just real quick. If you cross multiply these guys, you get yourself a 12a. I'm sorry, you get yourself a over here, a 12 over there, and then you just divide by sine of 35, and that'd be easy enough to get there. All right, and then we plug this in. Again, make sure your calculator's in degrees, and you should get it 3.9 feet, and that makes sense there. That can form a triangle. You can 12, 15 over here, 12 over here, and there's 13.9 feet right there. All right, the description to this problem sort of gives it away already here. Solving an SSA triangle, and then it says no solution. So then you kind of know what you are going to expect to find here. All right, let's go for it here. So it says solve, but let's see if we can solve in the first place. And so I'm going to put it like this, and then we're going to see if we have enough minimum value to reach to the other side over here. So angle A, angle B, angle C, that's the labeling. So that's 65 here, that's B is 30, and then A is 16. So the question is, based upon how wide this angle is and the length of the B value, do I have enough to get us back, at least minimally, to B? All right, we've got to do this by, there it is, B times the sine of 65. When we plug that in, we get ourselves 27.19 meters at this point, and that's not going to happen. You need at least 27.19 meters to get you back from C to B. We only have 16. That is going to be no triangle exists. Not possible to make that happen. All right, next one. Again, the description gives it away, the SSA, the ambiguous case, but we have one solution now. C is a acute angle. I'm going to set it up like this. Again, same exact setup. In this case, though, the triangle labeling has been switched. This is C over here. Now, if I know little a, if I know this, that kind of corresponds if I want to draw it the same way. So that corresponds to the fact that I got to label this as A, so therefore this would be little a. Last time we had a B over here, so got to make sure it corresponds, my diagram corresponds to the information given. Okay, if that's A, then that has to be B, and then the B value, or the C value is 50 feet, sorry. The A value is 30, so then the question is that enough to get you minimally to here? Well, hold on. Forget actually even guessing. Hold on, look at this. Notice that 50, not even guessing, but calculating the sine of 60 degrees times 30, because the C value is actually even larger than the A value. So that means for sure it's going to come down here. In fact, it's going to go way down here. You don't even need to calculate it because it's going to go way down here. So in this case, you only have one solution because when you swing it this way, it's going to be too much. It's not going to form the same triangle anymore, right? Because 50 swung back is going to give you 30 and then plus 1, plus 20 more. So there's no way it could form a triangle this way. When it goes this way, it's going to form one big triangle right here. There it is. All right, if you want to do it by the cases, I got to make the slide here back over here. So we have the acute angle case, and we have the case 4 right here. It's the fact that A is actually even larger or equal to B. In this case, ours is a little bit switched, right? According to the case here, our A value is actually technically the C value, and the B value is technically the A value. So you have to be able to switch those in your mind. All right, so technically it's case 4. Doesn't form anything here, forms one here. All right, and one little extra thing that we should talk about here. Let's see. Oh, is it case 4? Let me write that down. Case 4 is what we got here. So now let's redraw this triangle and start solving it here. So the one triangle case is like this. 60 is here, 30, 50. Labeling my triangle here. So sine of 60 degrees corresponds to 50 on the side, and then the, let me label this, so AC, AB, there it is, that's how it was labeled before. So sine of A, and then sine of 30. Notice I can't do B yet because I don't have no correspondence between the angle and its side. All right, with that, let's see, multiply both sides by 30. And then I'm going to have to take the inverse sine value to give me my angle measurement here. So really, angle A is sine inverse of all this stuff. All right, punching into a calculator here. I should get 31.3 degrees. Perfect. Okay, with that, because I know angle A now I think I can figure out angle B right away. I know the two angles already, therefore, adding them up, subtracting from 180, and that gets me 88.7 degrees. Perfect. Now I know my 3 angles inside the triangle. Looking for any other side that I need to know. Yep, little b, what I need to know. So how about sine of b, which is I know, over little b, which I want to know, over sine of c and little c. Okay, punching that in. Just the numbers, 88.7 now comes in finally. And I can cross multiply here. Let me cross multiply. It gives me b sine of 60 and 50 sine of 88.7 dividing by sine of 60. And eventually that gives me what I want. And it is 57.7 feet as you punch it into a calculator, and that makes sense. Notice that the correspondence is the bigger the side, the bigger the angle. Or so the bigger the angle, the bigger the side. It works both ways here. So if angle A is the smallest angle, being 31.3, should correspond to the smallest side. 60 should be in the middle. Since angle B is 88.7, it's the biggest angle, it should correspond to the biggest side. All right, so moving on, going to application right here as I think we conclude with application here. Bearings. How do we think about bearings? What does it mean to have bearings? And the problem, and navigation surveying uses them a lot. So a bearing is a measure of the acute angle from due north or due south, depending which way you go. So if you say a bearing of north 40 degrees east, means you're going north, but then you're going off to the right at a 40-degree angle. South 30 degrees west means you're going south, going down, and then you're going off to the right by 30 degrees. So let's see what that looks like. So just some quick examples here. There it is. So if you say north 40 degrees east, which means you're bearing north, 40 degrees towards the east. Again, north 6 degrees west, makes sense, going north, and then you're going to the left 60 degrees. Okay, going the other way, south, southwest 30 degrees, you're going this way. Again, southeast 75 degrees, you're going this way. All right, let's look at an example before we actually get to this. So a ship sailing due west at 20 miles per hour records the bearing of an oil rig. So we look at an oil rig and you're like, oh, look at that. The oil rig is looking north at 55.4 west. And then an hour and a half later, the bearing of that same rig, check it again, is 66 point east. Now it's on the east side. Okay, so how far is the ship from the oil rig the second time? So what's the distance? And then the next question is, how close did the ship pass? So let's go for it. So here's our two opportunities here. So point A right here is where the ship was. Notice the oil rig is up here, 55.4. And then a little bit later, it records the bearing again. Now it's north, but then it's 66.8 east. And so there's your legend for your directions there. All right, let's do some calculation here then. So if that's the case, let's see what we have here as far as some calculations here. So A, let's go now inside our triangle. That's what we want to do here. So if this is 55.4, you know the inside angle, angle A would be 34.6. If angle B, the outside angle, is 66.8. Inside, because these are going to be a perpendicular angle. These are all right angles, right? So if subtract from 90, that would be 23.2. So here's 23.2. Here's 34.6. Now, based upon those, can you get angle C? Absolutely, you can get angle C. Let me kind of write it in as we go so you can kind of see a little bit better visual. So that guy would have to be 34.6. This guy would have to be a 23.2. And then if you add these two up, then you get yourself 122.2, which is angle C inside that triangle. So having established that, the question is, how far? So how far is the boat away from the rig? So we got to figure out A. That's for, let's see real quick here. I'm going to read it here. How far is the ship from the oil rig the second time? So we want to find out little a. Then once we find that out, B is how close to the ship pass. Well, how close to the ship pass would be this little h value right here. It's the height that gets you a perpendicular line with the line. So we want to figure out when the boat was here, what really was the distance right here. Let's go for it. So do a law of sines for this one here. So the law of sines would be 122.2 corresponding to this side. Now the question is, what is this side here? Well, remember how the ship was traveling at 20 miles per hour, right? And then we wanted to figure out, and then they said an hour and a half later. So if it's an hour and a half later, that would be a 1.5 multiplier, or 30 miles. It has traveled 30 miles. So an angle and its opposite side, an angle which we know to be 34.6, and its opposite side, which is A. All right, so what do we got? It's approximately 20 miles away using law of sines. All right, then we got to find out the other one. And so now we have this set up then. Now we have this set up here. We're trying to figure out, oh, went a little too far. We're trying to figure out that h value. So this was approximately 20. The angle measurement here was 23.2. And now we need to use the definition formula for sine. The definition of sine is sine of my angle is equal to opposite side over hypotenuse. In that case, as we're solving for h, multiply both sides by a, plug in the values. So the closest the ship passed was 7.9 miles away from the rig. That's exactly what we think about. It gets more complicated if you go to astronomy. Now you're thinking about planets, you're thinking about curvature as opposed to straight lines. That gets even more fascinating. You know, asteroids passing by Earth, what is their trajectory? How close will they be? Will they actually hit our gravitational pull? I mean, all these things come into play, which is fascinating when you have to sort of think through all that. All right, for us, here's your problem as we finish it off. Practice problem number 8, last problem in the textbook for this section here, at least in the notes. So rework example number 8, assuming the second bearing is taken after 2 hours, so not after an hour and a half, but after 2 hours, and the bearing is given as north 60.4. So let's redo this again then. Let's go for it here. So bearing A, this is bearing A. So the original bearing of the oil rig, as we said before, was 55.4 degrees. Actually north, 55.4 west. The second bearing now, the changed bearing for us now, is 60.4 degrees. And the ship, our ship was going a little faster. It was going 25 miles per hour. So 25 miles per hour times 2 means the distance covered for us was 50 miles. All right, with that said, let's see what we know. So this side right here, the angle would be 29.6 because it's 90 minus 60.4. This angle, which is 55.4, now the interior angle would be 34.6. If I know those two angles, then I know the third angle as well. Let me just label this as a triangle now. And let's see, angle C would be the addition of these two angles together. And then the subtraction from 180. And if that's the case, how about 115.8 degrees is angle C? Again, calculate that. Stop the video if I'm going too fast. It's no problem. All right, based upon that information, now I can do whatever I want here. I want to know this dark area here. How far are we away from the oil rig at this point? So it'd be this angle corresponding to opposite side. It'd be this angle here corresponding to opposite side. Law of sines in the mix. Here we go. So sine of 115.8 degrees over 50, and then the sine of the 34.6 over what we don't know, which is labeled as x for us this time. All right, multiply both sides by x, 50, and then maybe get rid of the denominators here. I'm going to let you guys do that yourself just to make sure you guys can get to that right here. Solved for x would be 50 sine of 34.6 over sine of 115.8. And plug it in into your calculator most likely, and we'll get ourselves 31.5 miles. That's what we are. We are 31.5 miles away, which makes sense from our previous problem, because in the previous problem they were only 20 miles away, going a little bit, almost about 20 miles away. We were going faster this time. We were going 25 miles. So we were going faster, and plus we went for a longer time. In the practice problem, they only went for 1.5 hours, an hour and a half. Here we went for 2 hours, so 31.5 would totally make sense of the answer. Okay, now the question is this. How close did we get to that rig there? So I'm going to rewrite exactly what I have so I don't have to redo it again. This is part B. So the question is, how close did we get to this oil rig when we were passing by? All right, let's go for it. I'm going to drop this little guy right here. Boom. This thing right here is called the altitude, dropping it down. And with that, now we're going to figure out the rest. H is given. You know, it's 90 degrees there. And so what I'm going to use this x that I just figured out. I know that, and I'm going to use this angle here that I know. I'm going to use that, and then I'm going to use definition of sine. So sine of 29.6 degrees is equal to opposite side over the hypotenuse. In this case, we just figured out from the previous problem, it's 31.5. Multiply both sides by 31.5, and we get ourselves h is equal to 31.5 sine of 29.6 degrees. Punching into a calculator, and we get ourselves, that's what I got punched into my TI 83 plus, and voila. How about a 15.6 miles is the closest we got based upon our measurements here. So really, from the example problem that they had, we were way far away from that oil rig, a lot further out oil rig. Maybe the current drove us. We were actually actually more than twice as much passed by that oil rig. Anyway, so that is the end of 7.1. Hopefully that was sort of enjoyable to watch and useful and informative.